Hello dear students. The topic for our today is overfitting and underfitting. Our unit 3 is divided into three parts. First part deals with backpropagation algorithm, second part deals with overfitting and underfitting, and third part deals with keras. So today we are going to talk on overfitting and underfitting. We are going to see what exactly these are. Before we actually dive into that, we first talk on what exactly is generalization. Now, I don't think you are new to this term called generalization, where you have been learning about it when you have been learning about machine learning. So we know that if I talk on generalization, you already know that there is some samples on which a machine gets trained on. Suppose we take 80% of the samples for training and remaining 20% we keep it for testing, and we train our machine on 80% of the data, and we try to see that the machine is giving us optimum predictions on this 20% of unseen data. So we call this particular ability of the machine learning model or a deep learning model as generalization. So the ability of the machine learning to learn the real model of the data from the training set so that it can perform well on the unseen test set is called generalization ability. Now the second term that we are going to see today is about capacity. Now, basically, if I really want to talk on capacity of the model, then first I have to talk on the expressive power of the model. There can be two cases where the expressive power of the model is weak. When this does happen is that when does this happen is that when you have got a model with less number of layers. For an example, a single layer network, if it is, then it can only cope up with only linear model, or it can solve only linear problem. It may not be able to perform well on a non-linear model. So in that case, we are going to say that the expressive power of the model is weak. Now, on the contrary, I would say that the model's expressive power is too strong, wherein it will be able to train excessively good. That means for the training set, it is going to give you a very good performance, wherein it is even going to train about the noise that is present in the model, but perhaps in the same way it may not be able to perform very well onto the test set. It's going to have a poor performance, so we call it as the generalization ability is being weak. So now what exactly do we want exactly here is to find out what is model capacity. So if I want to say model's capacity, then the model's ability to fit the complex functions, you should have ample number of layers with you, and you should be able to fit in your complex functions properly. Your generalization need not be too weak, need not be very very strong, where it goes, again it is going to even predict for noise in the model. So we see that you are going to get a proper fitted model, and the major indicator of the model capacity is hypothesis space. Now, to understand that better more, we are going to see this particular example wherein we are going to observe a few samples of the data, wherein the samples of the data are taken as sin x, where x is belonging to this minus 5 comma 5. So you can see there are a lot of ways in which I can actually fit in this particular samples of the data based upon the degree of the polynomial that I choose to fit this particular function into. Now if I talk about model space, and in this model space, if I only search for say first degree polynomial, then I would say if I remove the bias, then I get the formula of a straight line for a first degree polynomial, which is represented by this orange line. Suppose if you want to increase your hypothesis space, now you don't want a first degree polynomial, rather you would like to increase the degree of the polynomial. For an example, if you can see, this is the curve that you have got for your degree number 5. Alright, for a degree 3 you can see there's a purple line, and then I'm sorry, for a degree 7 you can see there's a purple line. For a degree 3 you have got 3 line. Now if these are the samples of the data that you can see, I would like to say that with the human naked eye you may have some observational errors, which we are terming here with epsilon, and you always want to fit in a particular complex function that is suitably going to fit this particular samples of the data. So you can see this, the best fit curve that I can get it over the degree 17 of this particular hypothesis space polynomial function, then I could say that it is able to comply well with the samples that I have got with sin of x ranging from minus 5 to 5. So now next what we are going to see is, see here, so we are talking about the model capacity with respect to that particular function that we have just seen, that if you increase the degree of the polynomial, probably you could be able to fit in properly with respect to the samples, right? So you would say that you require ample amount of hypothesis space in order to get a better model capacity. But then there are certain disadvantages also if you use an excessively large amount of hypothesis space. So definitely, if you have got large amount of hypothesis space, it is going to be very, very costly in computation. Second, it is going to increase your search difficulty. Although you may have got a large hypothesis space, and with that you can fit it into properly into the complex function that is defining a number of samples, but it will not guarantee a better model. Of course, with the large number of samples or large number of hypothesis space, definitely the number of observation errors are also going to be very, very high, and it is going to hurt the generalization ability of the model. So you should always go for a moderation. That is the disadvantage of going with the large amount of excessively large amount of hypothesis space. Now let us talk about the concept that we really want now, that is overfitting and underfitting. So with that, the first thing that you have learned is what is exactly model capacity, and you should have a optimum amount of hypothesis space in order to get a proper model capacity. Now, because the distribution of the real data is always unknown, real time data, and it is quite complicated, it is impossible to deduce the type of the distribution function and its related parameters, of course. Now, therefore, while you are choosing the capacity of the learning model, you cannot exactly say that, oh no, optimally I'm going to pick up only this amount of hypothesis space because the data is not in my control. So people often choose a slightly larger model capacity based on the empirical values. So it's always better. Now, overfit. Now, when the here is the meat. When the capacity of the model is going to be too high, okay, when you have got large capacity of the model, then you may think that your model is going to perform better on the training data set. But if the same model, if it is performing well on the training data set betterly, and it is not performing well onto the test data set, then we call it as overfitting. Okay. On the contrary, when the capacity of the model is quite small, then in that case, the model will not even perform on the training set well. The model will, it is not going to, it is neither going to be performing well onto the training data set nor onto the test data set. So that is called as underfitting. So you can see here, this is the red vertical line which is going to show you this zone, particular zone. And this is called as an optimal capacity, wherein it is performing really well onto the training data set and also onto the test data set. But beyond that, if you are increasing your generalization error, your capacity of the model is becoming too high, and it is performing well onto the training data set, but it is not performing well onto the test data set. It is called as overfitting. And on the other case, when you have got the capacity too small, then in both the cases, both on testing and training, it is not going to perform well. This is called as underfitting. So you always aim for the optimum capacity of the model so as to avoid both of them. So now talking more on to the overfitting part. Again, I want to repeat that when the capacity of the model is too large, in addition to learning whatever the model training data set it is also learning additional observation errors or any other noise that is present inside your particular samples. So with resulting in the model performing better on the training data set, but it is not going to perform well onto the test data set or unseen samples. So in that case, we are going to say that the generalization ability of the model is not good, it is weak. So whenever you want to define overfitting, you would define that overfitting appears when the capacity of the model is too large, wherein the model is performing well on the training data set, but it is not performing well onto the test data set, and the generalization ability of the model is going to be weak. Then this particular phenomenon is called as a overfitting phenomena. So that's when we call that overfitting has occurred. So And on the contrary, what about underfitting? When the capacity of the model is too small so that the model cannot learn onto the modalities of the training set data well, which is going to result in poor performance both on the training set as well as on the test set. This phenomena is called as underfitting. So if you understand overfitting, underfitting is just a contrary part to it. Now for an example, you want to see in depth again, consider a 2-degree polynomial data distribution. You can see these sample dots onto your screen. These are your polynomial data, degree 2 polynomial data distribution. Now suppose if you are choosing your simple linear function, which is the straight line, so you can see the straight line is not crossing or not attempting to any of these samples that is present so far, correct? So this is a clear case of underfitting, wherein it is not even going to train well. It is not even going to perform good on the test data, because you can very clearly see where are the samples and where are you trying to fit in your complex data set, right? So your fit curve is not actually a best fit curve. It is underfit curve, wherein it is not even able to train properly, right? Forget about testing. So this is the clear case of underfitting. Clearly moving now, let us say for the same case, if you choose a very complex model function, in order to learn these particular data set, it is possible that this learned function is going to fit, but it is going to very excessively fit. It is even going to train all your observation error with it, any other noise that is present. So with that, what happens? Training, though it is going to give you perfect accuracy, but test set, it is not going to give you a proper performance. So this case is called as overfitting. Now what is best thing? This is the ideal case. So only when the capacity of the learned model and the real model roughly match, you are going to have a very good generalization ability, as you are seeing in this particular figure, wherein this is called as matching capacity, and the model is going to do good on towards your training data set as well as onto the test data set. So this was about overfitting and underfitting, what exactly it is and what should be the proper optimum capacity of the model. We are going to see solution for overfitting in our next class.